So, for anharmonic oscillator, we will see the vibrational spectra. Okay. So, you can, so what we have seen that this in case of anharmonic oscillator. So, this energy in wave number of course. So, this energy is V plus half omega e bar. Here I will write omega e, I think it is written 0, it will omega e bar 1 plus x e V plus half. So, x e is the anharmonic constant and V is vibrational quantum number. So, V can take value, V can take value 0, 1, 2, etc. right. And in this case selection rule, so for a harmonic oscillator selection rule was del V equal to plus minus 1, but in this case the selection rule is del V equal to plus minus 1, plus minus 2, plus minus 3, etc. Okay. So, now from this energy expression if you draw the energy levels. So, these are the energy levels, okay, defined energy levels, and you can see when for higher vibrational levels the separation of energy levels will decrease. From this expression one can see, just I have shown here. So, if this energy change due to the transition from E V equal to 1 to 3 minus E V equal to 0, okay, means from 0 V equal to 0 to V equal to 1, V equal to 2, V equal to 3, okay. If this transition occurs, so then what will be the energy of these spectral lines? So, that is del E. So, del E if you put V equal to 0 here and for V equal to V. So, E V minus E V equal to 0. So, you will get this expression, okay, del E equal to V omega E bar 1 minus V plus 1 omega E bar. Okay. So, this energy of these transition lines, so 3 cases I have calculated, V equal to 0 to V equal to 1. So, del E equal to omega E bar 1 minus 2 x e, just here you put V equal to 0, yes, no, V equal to 0 I have already put. So, here because V equal to 0 you have put. So, now V equal to this V equal to 1, 2, 3, 4. Okay. So, if you put 1, so 1 that means omega E here 1 minus 1 plus 1 2, the 1 minus 2 x e. Similarly, for V equal to 2 1 minus 3 x e and V equal to 2. So, V equal to 3 del E equal to 3 omega E bar 1 minus 2 plus 3 plus 1 4 x e. Okay. So, from here you can see that that energy levels here I have shown that separation will decrease with higher V. So, when transition from same level V equal to 0, so the spectral lines energy their separation will decrease because it will follow this separation, and that is what it is happening. So, this is the first transition line for V equal to 0 to V equal to 1. If it is for simplicity, if you neglect this part, you know, effect of x e. So, what you will see, this spectral line its energy is omega E bar. this one 2 omega E bar, this one 3 omega E bar, 4 omega E bar, etc. Right. But now these are the from these 2 omega E, 3 omega E bar, 4 omega E bar. So, basically this will be slightly smaller than that because of this term, because of this 1 minus 2 x u, 2 minus 1 minus 3 x e. Okay. So, because of this anharmonicity, otherwise what we could get? So, it could be equally spaced spectral lines, right, and separation would be omega E bar, okay, because it is the omega E bar. So, this could be omega E bar, okay, this omega E, 2 omega E bar, okay, etc. So, this separation would be omega E bar. So, all would be the equally spaced, but this is not the case because of this anharmonicity. Okay. So, this it's the slightly less than this 2 omega E bar. So, actual level will be here, actual level will be here, okay, is slightly less than 2 omega E bar. So, that is why the spacing between the omega E bar spectral lines in these vibrational spectra, okay. So, that will be gap will be smaller than the omega E bar, and it will increase for higher vibrational level, transition to the higher vibrational level. Okay. So, in case of harmonic oscillator, we have seen just only one spectral lines, and it has energy is omega 0 bar, okay. Now, in case of anharmonic case, we are getting this multiple number of spectral lines. So, these spectral lines, their separation is decreasing when we are going to the higher order of spectral lines, means for higher value of vibrational quantum number. Okay. So, so basically here, since the selection rule is del V equal to plus minus 1, plus minus 2, plus minus 3. So, that means transition from V equal to 0 to 1, 2, 3. So, that means it is V equal to change of this del V equal to plus 1, plus 2, plus 3. Okay. So, so due to the selection rules, we are getting this multiple spectral lines and this transition from the same energy levels V equal to 0 to the higher energy levels for V equal to 1, 2, 3. Okay. So, so these spectral lines we will see, and there is a I think this there are some names of these spectral lines. So, first spectral lines for V equal to 0 to V equal to 1, it is called fundamental lines or fundamental bands. So, why it is called band, that I will tell you later on. Band means it is not single line, it is a branch of line. Okay. So, why it is called band, so that I will tell you later on, and you will understand when we will go ahead. So, this is the fundamental band, and then this other one V equal to 0 to V equal to 2. So, that spectral line, this V equal to 0 to V equal to 2, this one. Okay. So, that one is called this first overtone band. Next one V equal to 0 to V equal to 3, this called second overtone band. Okay. So, these are the name of the spectral lines. Now, here just suddenly why I have shown the spectral lines, or I have shown the transition only from V equal to 0 to other levels. Why not V equal to 1 to V equal to 2, V equal to 3, V equal to 4. So, there should be another sets of spectral lines. Similarly, another set we could get this starting from V equal to 2 to V equal to 3, V equal to 4, V equal to 5, because there is no problem, because the selection rule will allow for all these transitions. So, so why I have not drawn that one, suddenly I have drawn these 3 lines here, all 3 lines, that's transition starting from the V equal to 0. Reason is that this it depends on the population of the energy level. Okay. So, how many population means, if you consider consider a quite large number of molecules, same molecules, but quite a large number of molecules in a system. Now, how many are there? So, they are in different energy states, they can be in different energy states. Okay. So, if you check that how many are in the ground state, means V equal to 0 state, okay, and how many are in the first excited state, that is V equal to 1, second excited state, etc. Right. So, so one can see that this at room temperature almost all molecules will be at the ground state, all molecules will be at the V equal to 0 state. Okay. So, that is what here this here we have I tried to explain that spacing between vibrational energy levels is of the order of 10 to the power plus 3 centimeter inverse. So, there is the basically spacing between the energy levels in case of vibrational energy levels. So, that is if it is delta E, if I write delta E. So, then at room temperature, so this as in case of rotation of a molecule, there we have seen this Boltzmann factor is used for this type of calculation. Okay. With this factor tells this basically the population at different levels. So, V equal to 1, so there n 1 number of particles or molecules, and V equal to 0, so n 0 number of. So, this n 1 by n 0 equal to e to the power minus. So, this E by k T, E here Hc del nu bar. So, it is in centimeter inverse. So, that is why one has to multiply with Hc for converting to energy, divided by k T. So, if you calculate taking this value 10 to the power plus 3 centimeter inverse, and other are constant, and it is at room temperature K equal to T equal to 300 Kelvin. So, if we calculate it is a 0.008, means it is a 0.01. So, it is just the 1% of N0, you know. So, whatever the number of total number of molecules, out of them only 1% molecule can be at the first excited state, means at V equal to 1, okay, and 99% molecule will be at the ground state, V equal to 0. Okay. So, this is the reason here I have shown this type of transition starting from V equal to 0, and at room temperature generally you will see this type of only this kind of spectra. Other spectra means from first excited state to the other excited state. If it transition from other excited states, corresponding the spectral lines that generally we do not see at room temperature. Okay. And reason is that if there is no molecule at V equal to 1, so if it is just less than 1%, so this transition transition probability for V equal to 0 to other excited states, excited levels, that is 99% higher than the transition from the V equal to 1 to the other excited states. Okay. So, even so this transition 1% transition will be there. Okay. So, compared to 99%, so intensity of that spectral lines which will come from V equal to 1 to the higher excited state. So, that intensity of the spectral lines will be very weak, or you can tell it is just intensity 1% of the spectral lines which is coming from V equal to 0 to V equal to 1. Okay. So, that is why these other states will not see in spectrometer. So, only this type of spectral lines we will see, which are, that is why this particular names was given. And also this here why we have given these names, because we will not see many spectral lines. Okay. We will see only few spectral lines. Okay. So, because this probability from V equal to 0 to V equal to 1 and probability from V equal to 0 to V equal to 2, this probability will decrease. Okay. So, the intensity will decrease when it is going from V equal to 0 to 3, 4, 5, 6 higher energy levels. So, this intensity also will decrease. Okay. So, we will see effectively very few lines, and those lines are called, as I mentioned, this fundamental band, first overtone, second overtone, third overtone, etc. So, so since they are few, so the name are given to them. Okay. So, next I will discuss that whether those transition from V equal to 1 to V equal to 3, V equal to 2, V equal to 3, or V equal to 2 to V equal to 3, V equal to 4, this higher transition between the different excited state, whether it is possible or not. Yes, it is possible. So, one has to increase the temperature of the system. So, you have a system of many molecules. So, if you increase the temperature, so then we see these some other spectral lines. So, what is the probability to have these other spectral lines? So, that is I have shown here just calculation, this say higher temperature, it is 600 Kelvin. So, for 600 Kelvin, if you just calculate, so this it is showing 0.1. Okay. So, 0.1 means it is 10%. Now, it is, you see this, when the system is at temperature 600 Kelvin, then the population of the states having quantum number V equal to 1. So, there this 10% molecules will be there. So, now there will be transition, means there will be transition, of course. Now, there will be more transition from V equal to 1 to V equal to 2, V equal to 3, and we will see the spectral lines. Although that spectral lines will not be very strong, it will be weak, but its intensity will be reasonable. Okay. So, one can detect that intensity. So, so increasing the temperature of the system, we can see these higher spectral lines, transition among the excited levels, and those spectral lines, since it is because of the heating of the system, molecular system, we get this type of spectral lines. So, that is why these spectral lines or band, spectral band, it is called hot band. Okay. So, so transition V equal to 1 to V equal to 2 will give spectral lines, okay, whose intensity will be 10% of the spectral line corresponding to V equal to 0 to V equal to 1. Okay. Because now population in V equal to 1, it is higher than the population was at temperature 300 Kelvin. Okay. It was only 1%, now it is 10%. So, we will get intensity. So, intensity will be basically proportional to the population. So, that is why we will get reasonable intensity, at least it will be 10% of this fundamental band. So, this bands is called hot band. So, this here I have shown you that this is the energy level V equal to 0, 1, 2, 3. Now, this transition, this already we have shown V equal to 0 to 1, V equal to 0 to 2, V equal to 0 to 3. Okay. So, these spectral lines as per the selection rule, these are allowed, and this one is called fundamental band, this one is called first overtone band, and basically this one is called second overtone band. Now, V equal to 1 to V equal to 2, as this intensity will be 10% of this one, but now it will be visible. So, this we will see only at higher temperature, and so that is why it is called V equal to 1 to V equal to 2, it is called first hot band. V equal to 2 to V equal to 3, it is called second hot band. So, we will see these spectral lines, and depending on their transition, whether it is from V equal to 0 or it is from V equal to 1 or V equal to 2. So, they are given some name. Okay. So, yeah. So, this basically here this for first hot band. So, this V equal to 1 to V equal to 2. So, this will be the energy or wave number of the spectral lines. So, this hot band. So, that is omega E 1 minus 4 x e. Okay. So, this one was omega E 1 minus 2 x e, this one omega E 1 minus 3 x e, that we have seen earlier. Okay. So, in this case also one can calculate what will be the frequency, what will be the frequency of these spectral lines. So, this for first band, first hot band. So, omega E bar 1 minus 4 x e, omega E bar 1 minus 6 x e, that will be for second hot band. So, one can calculate this. So, these are the basically band you will see, these are the band you will see for the molecules which have anharmonicity in their oscillation. So, basically that is the anharmonic oscillator model, and for that we have we have seen that this what will be the energy and spectral lines for this diatomic vibrating molecule. This basically anharmonic vibrating molecule. So, now from this study you can, if I take one example. So, from basically infrared spectrometer, using infrared spectrometer. So, one has to take the molecules. Okay. So, if I take HCl molecule, okay, and then this molecule will kept at a particular temperature. So, if it is room temperature, that is also fine. Now, we use spectrometer to see the spectra, okay, because all the time this transition is happening, Now, due to this transition, there are some radiation, infrared radiation. Now, we have to use spectrometer, okay. Spectrometer, you know, prism spectrometer, grating spectrometer, right, for visible light. I think you have used in lab, or you will use in lab. So, spectrometer, basically we have collimator, right. So, it collimates the light from the source. So, you have source. Now, this from this source, light is falling on this collimator. Now, through this collimator, this light will fall on the spectrometer table. On table, either we kept prism, or say grating, okay. So, when this light will fall on the prism or grating, so now there will be spatial separation, of these of the radiation of the light, okay, depending on their wavelength, okay. So, if you use white light, so white light have all sorts of color, wavelength, color. So, you will see the separation of all colors after passing through the prism or after passing through the grating, okay, and that we see. So, that is basically diffraction from grating. When you will tell grating, so there will be diffraction. So, diffraction phenomena is used to separate the light as per their, as a function of their wavelength, okay. So, the spectrometer is used to separate the spectral lines depending on their wavelength or energy or wave number, and that we see. So, we use telescope to see the spectra, okay, either prism spectra or the grating spectra, we use the telescope. So, this as a whole, this is called spectrometer. Spectrometer is having the collimator, and then table, prism table or grating table, and then this you have telescope, okay. And so, this the spectrometer, and spectrometer is used to measure the wavelength of the spectral lines, energy of the spectral lines, okay. So, in case of infrared, so if you need this, so you have to so you have to use infrared sensitive detector, okay, to sense the intensity, at okay, at in spatial resolution, in what is called to sense the intensity in space, okay. And in space you will get intensity, means different spectral lines at different space, because their wavelengths or energy are different, and that is why spectrometer does, okay. As for according to their wavelength or energy, it is spreaded over a space, okay. And so, this spatial separation is basically it depends on the energy of the spectral lines. So, infrared detector will be used to detect the intensity, okay, as a function of this this spatial distance, okay, and one can measure the energy or wavelength of the spectral lines. So, just I want to just describe the spectrometer. This is the standard spectrometer. Now, here I will use this one term absorption. So, generally infrared etc. we use the in this case we absorption spectra. Okay. Absorption spectra, this term I use, for that I explain the spectrometer. So, what we will do? So, white light, okay. So, instead of putting to the collimator directly, so white light will pass through the system of molecules. So, if HCl molecules, so assembly of HCl molecules in a glass tube, okay. Now, this white light means having all sorts of wavelength. Now, it will pass through this molecule gas, and then the light through this molecular gas, it will fall on the collimator. Okay. Now, from collimator to yours it will come to your spectrometer. Okay. So in spectrometer additionally I am putting a glass tube having the HCl molecules or other molecules. Okay. Now, white light was coming. Now, if any absorption happen in this gas tube, HCl gas tube, then that line will be missing in spectrometer, because there is no, when there is no gas. So, I will see this all sorts of wavelength. Now, I have put gas in the path of this white light. Now, there will be, if any transition in this HCl level, so there will be some absorption of this some radiation, okay, of wavelength. Okay. So, that wavelength will not reach, and that wavelength will be missing. So, that spectral lines will be missing, and then that will be, so in a white spectra of different color. So, there we will see dark line. Dark line means that radiation has not come, it is absorbed. So, that is absorbed by this HCl molecule. Okay. So, basically this way we in infrared spectroscopy or microwave spectroscopy, we generally study this absorption spectra. Generally we study the absorption spectra, and absorption spectra, this emission spectra and absorption spectra, these both are same. In one case it is emitting, that we are seeing, other case, okay. So, other case this from white light, so some lines are missing, some lines are absorbed. So, that absorbed by the gas, molecule gas, and that missing of the spectral lines, which we will see as a dark line, that we tell this is absorption line. Okay. So, here this term I have used, this HCl shows the absorption lines. Okay. So, from infrared spectrometer one can measure the spectral lines. So, fundamental lines, first overtone, second overtone, and it is measured for HCl, it is measured, and these are the values. Okay. And yes. So, I think I will stop here. I will continue this class, this discussion in next class. Thank you.